Hello, everyone. Welcome to the 95th online Spintronics seminar. It is my great pleasure to introduce today's speaker. Dr. Yassine Quessab is currently a postdoc researcher at New York University. In 2018, he received his PhD in physics from University of Lorraine in Nancy, France. Yassine was a member of the Spintronics and nanomagnetism team at Institut Jean Lamour under Professor Stéphane Majan's supervision. His PhD thesis work focused on the ultrafast magnetization switching of ferromagnetic thin film using femtosecond laser pulses, which was in collaboration with Professor Eric Fullerton's group at the University of California, San Diego. In 2019, Yassine joined Professor Andrew Kent's group at NYU, where he has been working on a DARPA project which aims to find the materials that can host the small and fast skyrmions. Yassine has been participating in several scientific outreach activities, for instance, as a program and organizing committee and advisory board member of the Around the Clock, Around the Globe 24 Hours Nonstop Virtual Conference in 2020 and 2021 during the pandemic. So without further ado, Dr. Quessab, please go ahead with your talk.
Yes. Yeah, thank you, Sin, for the very nice introduction, and thank you for giving me the opportunity to share my recent research work at NYU. And today I'm going to talk about the fast skyrmion dynamics in ferrimagnetic cobalt gallium thin films. And my goal today is to give you the keys to understand what are the parameters that control the skyrmion dynamics and how to tune the magnetic properties to achieve fast skyrmion dynamics, and also to understand what are the different trade-offs that come with fast skyrmion motion. So first, I will introduce the magnetic skyrmions and their application for high-performance computing, and then I will talk about these parameters that control the skyrmion dynamics and what are the different steps that we took to optimize the interactions in cobalt gallium thin films in order to achieve fast skyrmion dynamics that I will talk about in the third part of my presentation, and where I will talk about the current-induced formation and motion of skyrmions using nanosecond current pulses in cobalt gallium thin films. And then finally, I will mention a few perspectives of this work. So first, let me introduce the memory landscape. I think we are all aware that we have more and more intelligent and highly interconnected devices called the Internet of Things, and that leads to an exponential increase of the stored data and an increased need of memory solutions with high density of storage and a reduced power consumption. But the other aspect of it is that today's technologies are what I would call speed hungry. We need a faster access to retrieve the stored data from the cloud. We need faster computers, faster mobile phones, and so on and so on. And that really stresses the need for greater memory bandwidth devices, especially with the development of artificial intelligence and machine learning technologies. So the training process with AI algorithms generate a lot of data that is written and read many, many times. And so as a result, the memory device has a tremendous workload and it consumes a lot of power. So for an efficient AI device, it is necessary to have a memory device with a large density of storage and a reduced power consumption. And the other aspect of it is that the AI device needs to take the decision really fast. Think about a self-driving car. And so that is why large memory bandwidth to minimize latency is important. And as a matter of fact, magnetic memory, such as spin transfer torque MRAMs, are potentially a good candidate for that. Indeed, recently, a fast encoding of information in less than 2 nanoseconds was demonstrated, and MRAMs are well known to enable high density of storage with great data retention. However, the question is, can we have a memory device, a magnetic memory device that operates in less than 2 nanoseconds or even in the picosecond timescale? And as a matter of fact, domain wall and Skyrmion racetrack memories are potentially a good candidate, as they could enable high density and fast data storage. So the idea of a domain wall racetrack memory emerged a few years ago at IBM, where the data will be encoded using domain wall motion induced by Spintronics. And the domain wall motion will be detected using a magnetic tunnel junction. And then a few years later, that work was expanded to magnetic skyrmions. And I'm not going to go much into details in here because I believe you had a lot of talks before me that introduced this topic. But let me mention that I will be specifically interested in nail-type skyrmions in my talk. So today, STT-M runs have a switching time typically between 10 to 50 nanosecond, and that translates into a bandwidth of a few hundreds megabytes per second or a few gigabytes per second. Obviously, magnetic memories cannot compete with high bandwidth memory devices or other DRAMs. But the question is, can we have a faster SSD magnetic memory? And potentially there is room for a level 4 cache memory. And by combining skyrmions with MTJs, that could be a great solution. So STT-MRAM with MTJ pitch less than 50 nanometer is quite feasible and common. Now let's assume a skyrmion velocity of 500 meters per second, then the time delay between two consecutive MTJs is about 100 meters per second, and that gives 100 picoseconds, excuse me, and that gives you a bandwidth in the gigabytes per second scale. So what you realize is the key metrics for the viability of a skyrmion-based racetrack memory is the velocity, and that is why I specifically focused on this metrics in my research work. So most literature studies are done in ferromagnetic multilayers. However, ferromagnets have large dipole interactions, a strong pinging, and a Walker breakdown, which impedes the formation of small and fast skyrmions. And the maximum skyrmion velocity that is reported in the literature is about 100 meters per second. And in ferromagnets, the skyrmion dynamics is often associated with a large skyrmion angle between 20 to 50 degrees at the maximum skyrmion velocity. And it is actually desirable for technological application to suppress the skyrmion Hall effect, as it can lead to skyrmion annihilation at the edge of the racetrack and therefore to information loss. So in these studies, they have actually measured a velocity dependence of the skyrmion Hall angle. Well, in theory, it is predicted that the skyrmion Hall angle remains constant throughout the velocity scale. And that was explained by the presence of disorder, strong pinning site, and the formation of skyrmions in ferromagnetic materials. And that was actually observed in these X-ray images. So unfortunately, the skyrmion dynamics in ferromagnets is dominated by strong pinning effects and disorder, which prevents to reach high skyrmion velocities and lower skyrmion angles. On the other hand, ferrimagnets are attractive materials because of their weak dipole fields, fast spin dynamics, and the Walker breakdown can be eliminated at the angular momentum compensation. And they are theoretically predicted to host small and fast skyrmions. So I think a few weeks ago, you had a talk from Lucas that wonderfully explained the advantages of ferrimagnets. So I'm not going to go much into details, but in this ferrimagnetic cobalt gallium thin film, they measured a domain wall motion induced by spin-orbit torques with velocities of more than 1,000 meters per second at the angular momentum compensation temperature. And then in the same material, they observed sub-20 nanometer skyrmion, but unfortunately, the skyrmion dynamics was not studied in this paper. And then there's another study from South Korea where they investigated the current-induced skyrmion motion in ferrimagnetic multilayer system. However, they measured only relatively low velocities of about only 50 meters per second. So the fast Skyrmion dynamics that is predicted in ferrimagnets remains thus far elusive. So now I will talk about the different optimization and tuning of the magnetic interactions that we have taken in cobalt gallium thin films in order to achieve a faster Skyrmion motion. First, let me mention that there are a few quantities of importance for Skyrmion-based racetrack memory applications. So number one is the Skyrmion diameter, which determines the density of storage of the device. And the Skyrmion diameter depends on the TMI and the effective anisotropy, among other parameters. Then we have the lifetime, which determines the data retention of the device, and that is related to the thermal stability and energy barrier of the Skyrmion. Then the speed and the Skyrmional angle, which I've already talked about, and then the energy efficiency, which means how much power the device uses to encode information using Skyrmions. So the question is, how can we have small and fast Skyrmions at room temperature, and what are the different materials properties to play with for that purpose? So number one, we need a sizable interfacial DMI, which is good for the stability of small Skyrmions. It is desirable to have a low saturation magnetization to reduce the effect of stray fields and reduce even further the size of the Skyrmions. And then it is also desirable to have a low net angular momentum or spin density, which will play a role for fast Skyrmion dynamics. And that goes also with larger spin orbit torques and a low Gilbert damping. So in theory, the Skyrmion velocity is expected to scale linearly with the current density, with the Skyrmion mobility that depends on the net spin density, the spin orbit torques, and the damping parameter, among other parameters. So what you actually realize is that it is pretty difficult to satisfy all of these metrics at the same time. And the reason for that is because some properties will favor one metric against the other one. And so my goal is, by the end of this talk, you will understand why is that. And in this presentation, I choose to specifically focus on the speed, on how to achieve fast Skyrmion motion with a low Skyrmional angle. So the first step is a material study that we have taken, the growth and optimization and characterization of cobalt gallium thin films. And so cobalt gallium is a ferrimagnetic amorphous alloy composed of two anti-ferromagnetically coupled sublattices. The cobalt and gadolinium sublattices have a different gyromagnetic factor. And so that means that the magnetic and angular momentum compensation temperatures are different. We designed the cobalt gallium thin films in such a way that they are fully saturated at remanence, so that the nucleated Skyrmions are metastable, which is desirable for technological application. And that is in contrast with multi-layer systems that have a canted hysteresis loop, and where the ground state is already composed of a multi-domain state, or already with Skyrmions. So we characterize the DMI by Brunel scattering in collaboration with NIST Boulder. And I'm not going to go much into details about this measurement, but it is a spectroscopy measurement where the frequency shift between two spectra by reversing the in-plane field polarity is directly proportional to the DMI energy. And you can take these two papers for more information. So we measure the DMI in two systems. In one case, the cobalt gallium is inserted in between a platinum and a tungsten layer. And then in the other case, cobalt gallium is between two platinum layers. So when you look at the blue square data, you can see that the DMI is linearly proportional to 1 over the thickness. And that confirms the interfacial nature of the DMI in cobalt gallium tungsten. You can see that there is a small intercept, and there is ongoing discussion to know whether or not that could be associated with a bulk DMI in cobalt gallium. And actually, there is another recent work that measured a bulk DMI in a 50 nanometer gadolinium iron cobalt thin film inserted between two silicon nitrides. And that is the green star that I added in this chart. Now, when you look at the red data, cobalt gallium is between the two platinum layers, so it looks like the structure is symmetrical. You would not expect any inversion symmetry breaking and therefore no DMI. But we measured a significant DMI by BLS. And when we analyzed cross-sectional TEM imaging, we realized that there was some interface roughness and intermixing. And that can be actually a source of inversion symmetry breaking and therefore of DMI. The other thing that we realize is that if one wants to improve the current-induced Skyrmion motion, it is important to control the DMI and spin-up torques at the same time. And that is why we decided to study a tri-layer system to simultaneously vary the DMI and the spin-up torques. That is to say, the spinol angle. So in this case, the cobalt gallium, the ferrimagnetic layer, is sandwiched between two heavy metals with platinum at the bottom and another heavy metal layer at the top, and we changed the capping layer between tantalum, tungsten, or iridium. So the advantage of such a structure is that the bottom and top heavy metal layers, both of them are sources of spin-orbit coupling, therefore of DMI, which again favors the stability of skyrmions, and both of them are also sources of spin currents, and there is the possibility of having an enhanced dynamics. And the reason for that is because we purposely choose tantalum and tungsten because of the literature reports that indicate that these two heavy metals can have a giant negative spin Hall angle opposite of platinum. And so based on the chirality of the spin Hall effect, there is a possibility of having an enhanced net spin current. So we choose also iridium because there are some reports that iridium has a negative DMI contribution opposite of platinum. So with the same symmetry consideration, there's the possibility of having an enhanced net DMI through the cobalt gallium layer. So we choose the cobalt gallium alloys, alloy composition in such a way that they have a low saturation magnetization at room temperature, which means that they have a magnetic compensation temperature close to room temperature, which is ideal to achieve small skyrmions by reducing the effect of stray fields. With the alloy composition that we choose, the angular momentum compensation temperature is close to room temperature, and that indicates again, the possibility of having a faster dynamic. So here I show the temperature dependence of the saturation magnetization in cobalt gallium tantalum for 2 composition, and I show the magnetic and angular momentum compensation temperature corresponding to the blue square data. In collaboration with University of Virginia, we performed DFT calculation to estimate the DMI and the structures that we are studying. And unfortunately, cobalt gallium iridium had the lowest net DMI, and that goes against the literature reports that iridium had a negative contribution opposite of platinum. And we think that it may be due to the interaction between the gadolinium spins with iridium. And for more detail, you can check our paper. So here I summarize all of the magnetic properties that we measured as a function of the capping layer and the alloy composition. And so what we saw is that for tantalum and tungsten, these structures have the angular momentum compensation temperature that is the closest to room temperature, indicative again for faster dynamics, and they also have the lowest saturation magnetization at room temperature. So potentially these two structures are very interesting to study. Then the next step for us was to characterize the spin-orbit torques in these structures that I grew by DC magnetosputtering, and that was done by spin-orbit torque switching and also spin torque ferromagnetic resonance. I'm not going to go much into detail. You can check our papers for that. But we measured a Gilbert damping of 0.14 and then a net spin Hall angle of 16.5% for tungsten and 6.5% for tantalum. So in this study, we realized that cobalt, gallium, tungsten, or tantalum are the most promising structures to study fast motion of small skyrmions driven by spin-orbit torques because they have a sizable DMI that we experimentally measured by BLS and also a maximum net spin Hall angle of 16.5%. So here I summarize the magnetic properties of the films that we optimize. Again, they have a low saturation magnetization at room temperature, and then the angular momentum compensation temperature is about 292 Kelvin, very close to room temperature. And so that is why moving forward, we decided to focus on these two structures. So now the question is, once that we have optimized the cobalt gallium thin films, does it translate into fast motion of spin textures induced by spin-orbit torques? And so the first step for me to verify the quality of the films that I grew and optimized was to investigate the current-induced domain Hall motion in 5 nanometer thick cobalt gallium thin films, capped by tungsten or tantalum. And so the domain Hall motion was induced by a 5 nanosecond current pulse using a GSG probe as shown in this optical image. And this is the type of devices that I studied. Imaging is done by a homemade polymoke microscope that I built myself here at NYU. So this is the GSG probe that sends the RF wave into the device, the objective lens, the sample is clamped onto the transparent window, and then on the back side there is a projected electromagnet. So here I show a sequence of differential moke images before and after sending a train of positive current pulses and negative current pulses. So for the rest of the talk, a red pulse indicates a positive current pulse, and a blue pulse indicates a negative current pulse. And the bright contrast indicates a magnetization up domain, and the dark contrast indicates a magnetization down domain. So you can see that after sending a train of positive current pulses, the domain wall moves downward, and after a negative current pulses, the domain wall moves upward. So the domain wall displacement direction reverses by changing the current polarity. And when you look at these two first images, you can see that down, up, and up, down domain move in the same direction, which is consistent with spin-orbit torques-driven motion of male domain walls. And then from there, we can measure the domain wall velocity as a function of the current density. And so these are the results. We measure the maximum domain wall velocity of about 448 meters per second for tantalum and 460 meters per second for tungsten. And in this domain wall motion measurements, we can distinguish several regimes. So at low current density, we have the creep regime, then we have the flow regime where the domain wall velocity is proportional to the current density. Then we have the saturation regime. And surprisingly, we observed at very large current density a decrease of the domain wall velocity that we attribute to the Joule heating induced by the injection of the current pulses. So I am again going to refer to Lucas' paper where the domain wall motion induced by spin-orbit torques is well detailed based on the one-dimensional model adapted for ferrimagnets to take into account the net spin density. And you can see that the domain wall velocity plateaus when you have a non-vanishing net spin density. And the saturation value of the domain wall velocity depends only on the GMI and the net spin density. Let me mention that within our cobalt gallium wire, we never observed domain wall nucleation inside the wire, and actually domain wall nucleation was pretty hard to achieve, and that indicates that our films have a very large nucleation field and also a low density of pinning sites. And so that, together with the fast velocity that we reported, we can say that our cobalt gallium racetracks have a very low domain pinning and density of natural defects, which means that the structures that we optimize are ideal to study skyrmion motion. So before studying skyrmion motion, one needs to nucleate skyrmions. So how did we do that? So we've done two different types of experiment. The first one was in the polar Moog microscope, in the similar geometry that I've shown before for the domain one motion. Here we send a amplified current pulse with a GSG probe, and then we take an image before and after sending the current pulses, and these are the results. So we were able to nucleate skyrmions by applying a single 5 nanosecond current pulse at 0 magnetic field. So a circular bright region indicates a skyrmion with a core pointing up, and a dark circular region indicates a skyrmion with a core pointing down. What is surprising is you can see that in these four images, that regardless of the initial direction of the saturation, magnetization, and the current polarity, we were always able to nucleate a skyrmion. And so we can rule out a nucleation process based on spin-orbit torques or Orchard fields, but it rather points out that the nucleation is a thermal process. So the second experiment was done in exactly the same type of film, but deposited on a silicon nitride transparent window and imaged by X-ray microscopy that was done at the Swiss light source. So the geometry is slightly different. The amplified current pulse is collected by an oscilloscope. And so we were also able to nucleate skyrmions, but this time with a train of 5 nanosecond current pulses, and again at 0 field. And again, you can see that the nucleation does not depend upon the initial magnetization direction. And these skyrmions have a diameter of about 200 nanometer. So what are the differences between these two experiments? So on the left side, it was done in the polar Moog microscope with a single 5 nanosecond current pulse, and that leads to larger skyrmions of about 2 micron radius. Interestingly, these skyrmions had a very low lifetime of about a few seconds to a few minutes. On the other hand, the skyrmions that we were able to nucleate and these structures in image by scanning transmission X-ray microscopy had a much larger lifetime of more than 12 hours. And this nucleation was done by sending 100 5 nanosecond current pulses. So after that, I studied the skyrmion motion in the polar Moog microscope. And so first I nucleate skyrmions at 0 magnetic field, and then I apply a small negative out of plane field to stabilize the core of the skyrmion. And these images are taken after sending a single current pulse. So you can see here that after sending a positive current pulse, the skyrmion moved downward, and after sending a negative current pulse, the skyrmion moved upwards. And so the skyrmion displacement changes when reversing the current polarity. Now let's look at skyrmions with the core pointing up or down, and after sending a positive current pulse, you can see that in both cases the skyrmions move downward and in the same direction. And that confirms that the skyrmion motion is indeed induced by spin-orbit torques, and these are nail-type skyrmions. So these Moog images were taken in 5 nanometer thick cobalt gallium tantalum, and that corresponds to a velocity of about 400 meters per second. Interestingly, you can see here that after the third current pulse, the top skyrmion disappeared, and that is because we observed stochastic annihilation, and that we think that is due to the Joule heating, because again, these larger skyrmions have a very short lifetime, that is indicative of a smaller energy barrier. And unlike in ferromagnetic materials, here we haven't seen a strong deformation of the skyrmions, but rather a shrinking of the skyrmion, as you can see in these images. So now we can measure the skyrmion velocity as a function of the current density for cobalt, gallium, tantalum, or tungsten. And so we measure the maximum skyrmion velocity of about 610 meters per second and about 500 meters per second for cobalt, gallium, tantalum. And so these are the highest skyrmion velocity reported thus far in the literature. So skyrmions move faster in cobalt, gallium, tungsten than cobalt, gallium, tantalum. And because our sample has a non-vanishing net spin density, we expected to observe a plateau, but the plateau was only short-lived, and we again observe at large current density a decrease of the skyrmion velocity that we attribute to the Joule heating due to the current pulse injection, which would result in an increase of the net spin density because the angular momentum compensation temperature of our film is below room temperature. And when the net spin density goes up, the velocity goes down. So in blue here, I show the flow regime, and we were not able to measure the creep regime because we cannot apply current pulses smaller than 0.7, 10 to the 12 amp per meter square in our setup. And so obviously with this behavior, we can say that the skyrmion motion again deviates from the TL approximation, and we cannot completely consider the skyrmion as a rigid spin texture. The other metrics that is important for technological application is the skyrmion Hall effect that one needs to suppress to avoid information loss. And that's what we studied also in our cobalt, gallium thin films. So by tracking the coordinate of the spin textures that we nucleated in the MOC after sending a current pulse. And that's what I show here in figure E. That is the tracking of 3 spin textures. And you can see that there is a transverse displacement with regards to the current pulse injection direction. And between A and B, we applied a train of positive current pulse. And you can see that the skyrmion moves downward and to the left. And between C and D, we applied a train of negative current pulse, and you see that the skyrmion moves up and to the right. So by reversing the current polarity, the deflection angle does not change. And that confirms that this transverse displacement that we observe and measure is indeed a result of the skyrmion Hall effect. And the skyrmion Hall effect is a direct consequence of a non-zero topological charge. And as a consequence, we can say that the observed spin textures in the MOC are indeed topological, and that is why we can call them skyrmions. So we measure the skyrmion angle as a function of the skyrmion velocity for our 2 samples, and we measure the very low skyrmion angle of about 3 degrees. That is actually much lower, again, than in ferromagnets. Again, in these studies, they observed a velocity dependence of the skyrmion angle, while in our study, the skyrmion angle seems fairly insensitive with regards to the velocity that we measured, even though that is 5 times or 6 times larger than in ferromagnets. And again, this velocity dependence was explained by disorder and deformation of skyrmions. So it appears that skyrmion dynamics in our cobalt gallium thin films is not dominated by disorder. There's also another recent study that has shown the vanishing skyrmion angle at the angular momentum compensation temperature. And so that gives us another explanation of why our skyrmion angle is much lower than in ferromagnets. And that is because we have a very small net spin density, with the angular momentum compensation temperature being close to room temperature. And actually, the net spin density is about 2 orders of magnitude smaller than a pure cobalt film. One could argue that the reason we observed a low skyrmion angle is because the diameter of the skyrmions that we have is very large. But if one were to scale the value based on the magnetic properties that we measured in our cobalt gallium thin films for 200 nanometer skyrmion, we would still find a skyrmion angle that is much, much lower than in ferromagnets. And again, for a velocity that we measure that is 5 times or 6 times larger. So before concluding, I want to compare the domain wall and the skyrmion motion induced by spin-orbit torques. So we found out that skyrmions move faster than domain walls, which is quite surprising. And here I summarize some important metrics, that is the mobility and the depending current density for domain walls and skyrmions as a function of the capping layer. So cobalt gallium tungsten has the largest domain wall and skyrmion mobility, with a skyrmion mobility of about 900 meters per second per current density value. And that can be explained because cobalt gallium tungsten has a larger DMI and a smaller net spin density compared to cobalt gallium tantalum. So now I want to take a step back and look from where we went from the optimization of the interaction in cobalt gallium thin films that led to the fast skyrmion motion at room temperature that I have just reported. So our approach was to use 2 heavy metals on both sides of the cobalt gallium in order to increase the spin-orbit torques. The downside of this approach is that it reduces the net DMI, and that results in a larger skyrmion diameter. And also, we choose a very thin cobalt gallium layer of about 5 nanometer, and that also not only, the 5 nanometer thick cobalt gallium layer will help to maximize the spin-orbit torques, but it also leads to a larger skyrmion diameter and also to a smaller lifetime. So with that, you really see that it is difficult, like I said at the beginning of my talk, to satisfy all of the metrics at the same time, even though that we had a very low saturation magnetization in our films, and that one needs to make some compromises in order to satisfy one of the metric. And so the fast skyrmion dynamics of really small skyrmions is still an open challenge, but we showed that cobalt gallium is an excellent candidate. And I have a few ideas of how to overcome the obstacles. That is to not only have a smaller skyrmion, a faster motion, and also a larger lifetime. But let me just mention 2 routes that one could take. So here I am showing a theoretical paper from MIT where this is a phase diagram for the skyrmion diameter as a function of the DMI energy and the magnetic layer thickness. And then the yellow star indicates our cobalt gallium thin films. So at a fixed magnetic layer thickness, if one were to find a way to increase the DMI, you would see that the skyrmion diameter will go down. The other possibility is to increase the magnetic thickness. So of course that would lead to a decrease of the DMI, but it will also decrease the skyrmion diameter. And you understand that when you increase the thickness, you will also decrease the net spin orbit torques and the net spin currents. So really, it is important to find that sweet spot and that compromise between large spin torques and large DMI. And then also the larger thickness of the ferrimagnetic layer will also have to have a larger energy barrier for the skyrmion and therefore a more stable skyrmion, which is good for obviously data retention. So to conclude, we demonstrated zero field nucleation of skyrmions induced by a single 5 nanosecond current pulse. We showed that the skyrmions in our films have a very large mobility with a velocity of up to 610 meters per second at room temperature. We showed that the skyrmion motion is induced indeed by spin orbit torques. We were also able to nucleate 200 nanometer skyrmions by a train of 5 nanosecond current pulses. We showed evidence that the nucleation is a purely thermal process. We confirmed that the spin textures nucleated in the Moog microscope are indeed skyrmions, thanks to the observation of the skyrminal effect. And we measured a very low skyrminal angle that is much lower than in ferromagnets, with a skyrminal angle of about 3 degrees. So I just want to mention that currently our manuscript is under consideration, and if you have any question, please send me an email. And here I would like to acknowledge all of our collaborators at NYU, at University of Virginia, also at Swiss Light Source, where the X-ray imaging was performed, and this Boulder and MIT. And with that, I would like to thank you for your attention. I'll be glad to answer any of your questions.
Thank you very much for this very interesting talk. We can use the reactions buttons to thank the speaker. This talk is open for questions. If you have any questions, please raise your hand using the raise hand button on the reactions. Or if you're watching this on Twitch, you can just type your questions in chat box and I will read it for you. Do we have any questions on Zoom? We can start with a few quick questions and then we'll ask Kirill. The first one is actually, you say 5 nanometer of the cobalt gadolinium is actually thin. I wonder why can't you just make it 2 nanometers or even thinner?
So it is said that cobalt gadolinium has a bulk anisotropy. So if you were to go too thin, the magnetization of the cobalt gadolinium will fall in plane.
I see. So you have to grow at least the 5 nanometers in order to get it perpendicular.
Yes, I think you can push it a little bit down to 3.5 or 4 nanometer with some very skillful optimization, but it is pretty hard.
I see. Great. And I have actually a related question. In this experiment, you're using the alloys. So there's a cobalt gadolinium alloy fabricated by co-sputtering, I suppose. You can fabricate ferromagnetic with bilayer structures. Do you see any disadvantage of doing that? So one layer of cobalt and then another layer of gadolinium. And maybe you can even coat another cobalt as long as you can control the relative thickness. That may help increase the DMI, though.
Yeah, actually, yeah. I mean, it's true that if you do these bilayers, you add more interfaces. So it may help with the DMI, I guess, maybe. But I'm not so sure about the spin currents, because I guess at each interface, you may get some reflection or some losses. So I'm not so sure at the end if exactly the bilayer would be more beneficial compared to an alloy.
I see. Sure. Yeah. Thank you. Kirill, please go ahead with the question.
Yes. Thanks for the interesting talk. I have a simple question. So you showed the plot of the Skyrmion velocity as a function of the current density that saturated. And you said it's because of the Joule heating that moves you away from the compensation point. So if you took a different concentration so that the compensation point was higher than room temperature, so that you would actually approach compensation with higher current density, would you expect like a super linear growth and potentially higher Skyrmion velocity?
Potentially, I would say. Because of course, all of the interesting properties and fast dynamics happens at or close to the angular momentum compensation temperature. So I think we estimated with by COMSOL simulation that at very large current densities, we have a temperature increase of about 50 K. So, so I think that's what you would have to keep in mind is you would have to have a low composition so that the angular momentum compensation temperature is about 350 K in that order. So yes, to answer your question, I would expect that with the heating induced by the current, as you get closer to that, the velocity should remain linear or goes even larger.
Yeah. Thank you.
Great. Do you have any other question? Carlos has one question. Let me read that to you. I wonder what is the angular compensation temperature in your sample?
Yeah, let me go back to the table. So go full screen. So these are the two samples that we choose to study for the Skyrmion motion. So for copper, gallium, tungsten, it has a angular momentum compensation temperature of 292 Kelvin and magnetic compensation temperature of 250 Kelvin.
Thank you. I hope Carlos that answered our question.
Yes, thank you. Thank you. May I one more? Can you tell us how do you measure the angular compensation temperature on the sample?
So so we do VSM measurement of the MS, right, as a function of temperature. So the magnetic compensation temperature is experimentally measured. Then you have a parallel model, and you can deduce the angular momentum compensation temperature from that model, because the fact that the gadolinium and the cobalt has a different gyromagnetic factor, and the temperature dependence of the net moment, by doing a fitting of this curve, you can deduce the exponent factor attributed to each sublattice, and then you can deduce the angular momentum compensation temperature. And let me mention that there are a few studies that they extracted the TA from VSM measurements, and they also measured the TA with domain law motion as a function of the temperature. And the two values were pretty consistent.
Right, but so in this model, you need experimentally TM and TC. Have you measured TC also, or you take that value from VAL?
TC was assumed to be 450 Kelvin.
Okay.
Which was based from other literature studies.
Thank you. Nice talk, Yassine. Nice work.
Yeah, unfortunately, our PPMS VSM cannot go above 400 Kelvin, so I cannot experimentally measure TC, but I think probably in non-C you can, I guess. So
no, it's difficult. We try with covalterium. I mean, when you heat up the ferrimagnet, you lose the property about 500
exactly.
Kelvin. So yeah,
yes,
it's pretty tricky.
Great, thanks for the question. Professor Te Yu-Jian, please go ahead with the question.
Thanks for a very good talk. I just have a kind of pretty general question. So many of the Skyrmion system, they are in certain range in their phase diagram. So you can tune, a certain range of temperature, magnetic field to still have Skyrmion. Does that actually affect the velocity of the Skyrmion? Like a different location inside the phase diagram that you have a Skyrmion phase?
Could you repeat the question again, please?
So what I'm saying is
that
so typically Skyrmion in some system that exist a certain range in the phase diagram. And phase diagram typically can be a certain range of magnetic field and temperature range, right? And but within that phase diagram, if you tune to different temperature or magnetic field, would you expect to see the velocity of Skyrmion change?
I would say yes for several reasons, because I guess that way, depending on where you are in your phase diagram, the Skyrmion diameter will be different, and the velocity depends on the Skyrmion diameter. So there'll be one aspect of it, and I'm sure that depending on your magnetic field value, that should also have maybe a small contribution to the velocity.
So the question is more like how big deviation if you expect would be.
I mean, that I don't know, but in my experiment, I try to always have a very, very small bias out of plane field for the motion. It was only 5 millitesla, and I think if you look at the literature in ferromagnets, they usually have 30 millitesla or so. And so, I mean, of course, if you were to have more stable Skyrmions, you could, do everything at zero field.
Right.
I was able to nucleate at zero field, but for the motion, the stability is really important. So that's why I applied a field.
Thank you.
Okay, great. Do you have any other question? Ze Xianghu, please go ahead with your question.
Can you hear me?
Yeah.
Okay, thank you. Thank you very much. Very, very nice. I don't work on Skyrmion, so I have a very simple question on the conclusion slide. On the conclusion slide, there's a sentence. At the very beginning, I have a question. I say, okay, how could you distinguish the Skyrmions and the normal domain or domain wall? But after I read the latter sentence, you say the Skyrmion's nature was confirmed by observing of the Skyrmion Hall effect. So does that mean if Skyrmion there's an angle, but if for the normal domain there's no that angle? Is that right?
So, I mean, the fact that you observed a deflection of during the motion, that is indicative of the Skyrmion Hall effect. And so when you look at the equation of motion, the deflection is due because you have a non-zero topological charge. So if you had, let's say, a magnetic bubble, so that the winding number gives you topological charge of 0, you should not observe a deflection during the motion. But since we observed a deflection during the motion, it tells us that the object that we were looking at are topological, and that is why we can call them Skyrmions.
Okay, so you mean for the normal domain, so the deflection should be 0. Is that right?
Yeah, exactly.
Okay. Yeah.
Yeah, if you look at these images, if
I remember this image. Yes, yes.
If that object was not topological, then it should move in a linear fashion. I mean, I guess you could have some edge effect, but that is why here I reverse the current polarity, and then you see that between these two images, the deflection angle does not change. So it confirms that this transverse displacement is really due to the Skyrmion Hall angle, the Skyrmion Hall effect, and it is not some weird edge effect.
Okay, I see. Yeah, thanks so much. Thank you. Yeah, thank you.
Great. I'm going to butcher the name, but Gunashil, please go ahead and ask your question.
Hi, thank you. You didn't torture the name, actually. It's good. I have a question. So thank you for the nice talk. So my question is, you cap the layers with either tantalum or tungsten, which are both opposite spin Hall. So I suppose it's to enhance the spin orbit torque, but also for DMI. But does it matter if either of these, they get oxidized, because both of these are known to oxidize, right? Or does it not affect or do you not care about this for your measurements?
No. I mean, cobalt gallium is very sensitive to oxidation. Gadolinium atoms tends to chemically absorb oxygen, and you might get a oxidized layer at the interface, and then your cobalt gallium will fall in plane. So that is why all of our samples are capped by platinum. So we have cobalt gallium, tungsten, and then platinum at the top.
Okay. And I have another question. So, I mean, Stixum is element sensitive. So I was wondering if you looked at the other edge to see if there are any differences either in the skyrmion or the motion, or they're just always coupled antiferromagnetically.
We've done only the measurements at the cobalt edge, simply because of lack of time.
Yeah.
Time is very limited in synchrotron, unfortunately. Yeah.
Yeah, that's all. Thank you.
Thank you for the question. Golam Moshe, please go ahead.
Hi, Yassine. Very nice talk.
Hi, Golam.
Yeah, I'm just wondering about like in the method of calculating the velocity where you show the experiments. So the two different methods you showed, and with two different capping there, like for tungsten you do one measurement, and for tantalum you use another method. Is there any specific reason for that?
Can you repeat the question again? You said
so when you talk about the experimental measurement for velocity, so you talk about two different methods, right?
Two different what you said?
Two different experimental setup or two different methods?
No. It's the same method. It just I swap the samples. So
okay. Yeah.
It's just like I have one sample, and then I do a bunch of measurements for a few weeks, and then I change, and then I put the one with tantalum, and then I repeat exactly the same procedure.
Oh, okay. Yeah. Sorry, I misunderstood that. Yeah. Thank you.
No problem.
Great. Do we have any other question? I don't think we have any other questions. If you have further questions, we still have a session afterwards that you can discuss with the speaker. But at this moment, I want to thank the speaker again.